In this segment, we're talking about solving one-step algebraic equations using the manipulatives. It's important to note that anytime that we have an equation, we have an equal sign. And as soon as I put an equal sign in my equation, I automatically produce a left side of my equation and a right side to the equation. Understanding that there's a left side and a right side with the equal sign being the determining factor of where those sides are is extremely important in understanding what we're doing. If there's no equal sign, then we don't have an equation. We have something called an expression. And you cannot solve an expression. You can simplify it, you can expand it, you might factor it, but you cannot solve it, because to solve means that you're missing a piece. So to solve an equation means there must be a piece that is missing in my equation to make the left side equal the right side. And in order to solve it means I have to find out what that piece is that's going to make the left side equal the right side. Because we have the two sides and they're equal, we can often say that they're balanced. And when you read in textbooks, lots of times you'll see a balance beam or a teeter-totter being used. And I'm going to use a teeter-totter because most students have been on a teeter-totter. They may not have used a balance beam. And so most kids on a teeter-totter understand that if you put something on one side of the teeter-totter, you have to put something of equal size on the other side. And it should be about evenly placed too, because if something's way off this side, they're not going to be equal. The teeter-totter won't stay balanced. So as soon as we put an equal sign, it means that we have a left side and a right side, and that they are already started to be balanced. When I add a piece that I don't know, now I have to figure out what has to go into that piece, and that's my variable, and we're going to be using the letter x to be signifying our variable. The other thing we have to remember is when we do something to an equation, we do something to an entire side. Sometimes it looks like we're doing it to just one piece of a side, but we're actually doing it to an entire side, and I'll come back to that later, because we can only do things with like terms if we're adding and subtracting. If we're multiplying and dividing, we don't do it with a like term, so we're going to do it to an entire side. So it's very important that students understand that we do things to entire sides, not just to pieces of a side. So let's start off with this question, x plus 1 equals 3, and notice I've lined my equal sign up with my center of my fulcrum. So there's more things on this side than there are on this side. So we have to factor that in a little bit. So for my drawing, I have something that I don't know, plus a 1, and I'm going to equal 3 of the things on the other side. And we've already talked about what these things are. These are my 1 squares, so I'm going to keep them as that. And I'm going to use the algebra tiles. Sometimes we can use chips and things like that, but I'm going to use the algebra tiles because in my sequence of videos I'm going to go all the way up to high school, so we're going to keep using these tiles as they are. Now in order to solve my equation, I need to find out what is in this unknown box here for x. So in order to do that, I need to have x all by itself on one side and my answer over here on the other side. So I need to, another way of thinking about it is to isolate my variable. So one of the ways I could do this, I can see that if I just take this box away, I can get my x by itself. So if I take the box away, but then I can't do that. But I haven't done the same thing to both sides. So if I take a box away from one side, I have to take it away from the other side. And this could be called pair removal, or removing a pair. And whatever, if I remove a pair from one side and if I remove a single from one side and a single from the other side, as long as I remove the pair, then I'm okay. And my answer would be left with x is equal to 2. And students would have no problem with that because they know that 2 plus 1 is equal to 3. The problem is, though, is you say you must show work. And they go, well, why do I have to show work? Because I know that 2 plus 1 equals 3. Well, we're going to start off with some easier questions. And as questions get harder, that work becomes more important. So what kind of work would we show for what we just did there? So this is one way that we could show that we've removed a 1. We removed a 1 from both sides. So what I'm going to show here is I started off with my x plus 1. There it is right there, x plus 1. And now I had to remove a 1. So I'm going to put it there, and I do the same thing to the other side. Now, did I remove the 1 from the x, or did I remove the 1 that was by itself? Well, I remove the 1 by itself. So I can combine these two things because they're the same kinds of things. And I can combine these things because they're the same kinds of things. And so I'm left with x by itself is equal to a 2. Now the other way, here's my original question again, x plus 1 equals 3. The other way that I could show this is I could remove this 1 positive by adding a negative. If I add a negative, that's going to produce a 0 pair. And whatever I do to one side, I have to do to the other side. And so now what I've got here is I've got a 0 pair here, and I've got a 0 pair here. So effectively what I've done is I've removed these two pairs, and I'm left with x equaling 2. So how do I go about showing in my work that I added a 0 pair? And I can show it this way. I have my x plus 1, and I added my negative 1. And so if I added a negative 1 to one side, I have to add a negative 1 to the other side. And that produced a 0 pair. A positive 1 plus a negative 1 is a 0 pair. And so 3 plus negative 1 is 2. And so I could show that I've added a 0 pair this way. And this goes back to our discussion when we were talking about integers, about does that negative sign mean a subtraction or does it mean a negative? And it can be working both ways. So I'm adding a negative or I'm taking away. It can be written in both ways. Here's my next question. X minus 2 equals 4. So I've got an x and a negative 2 on one side and 4 positives on the other. I want to remove my two reds. So there's a couple of different ways that we can do this. I personally like the idea of making 0 pairs right off the start. So if I want to make this into a 0 pair, I need to add a green. So whatever I do to one side, I have to do to the other. And if I want to get rid of this red, I have to add a green. And so therefore I have to do the same thing to the other side. Now this is going to produce two 0 pairs. And so those effectively are gone. And so what I'm left with now is x is equal to 1, 2, 3, 4, 5, 6. X is equal to 6. And there's the work I would show with that. My 0 pairs are gone. I now have 6 on this side. So I started with x minus 2. And now I've added a 2 to it. And whatever I did to one side, I did to the other. And it gives me x equals 6. Is there another way of doing it? Yes, there is. And I'll show you that right now. So here I am with my original question, x minus 2 equals 4, and I've put our separate piece over here, so we're just going to work down. So I'm going to show you another way of doing this. So what I want to do is I want to remove my two reds. But I can't remove two reds from this side because I don't have any two reds on this side. So what I could do is I could put some 0 pairs over onto the right-hand side. And by doing that, I haven't changed anything. I still have x and negative 2, and over here I have 4, and these are still zeros, so it doesn't matter. Again, this is a perfect example of students really need to understand their integers before they can go ahead and start working on this. If students are struggling with their integers, then you might as well go back and work on your integers because this is just going to be very difficult for them. So now we've got our 0 pair, so we can effectively remove these ones over here because these are 0 pairs if I wanted to get rid of them, but I don't. I want to remove the two reds. So if I pull my red from here, I can do the same thing from this side. If I pull a red from here, I can do the same thing from this side. So I've done that paired removal process that I did before, and either way I get my answer of x is equal to 1, 2, 3, 4, 5, 6. I still get my answer of x equaling 6, and the work that I want to show would be a little different as far as my picture goes, but as far as my work goes, it's still the same. I had x minus 2, I added 2 greens to this side, and I added 2 greens to this side. So there they are right there. There's my 2 greens I added to this side. This produced a 0 pair, so they went away over here, and this produced a 6 on this side. So my answer would still be x equaling 6. In this question, it's the same kind of deal. 1, 2, 3, 4, 5 is equal to x plus 1, so 5 equals x plus 1. Yet, students will have huge amounts of difficulty. This will just be very confusing for them for some reason. They are so used to seeing the x's on the left side of all of their questions, x plus 2 equals, or x plus 3 equals, or x plus whatever equals, and the x is always on the left-hand side. Throw the x on the right-hand side, and it's amazing how confusion reigns supreme. Now as far as solving it, it works exactly the same way. I want to get x all by itself. It's over here on the right side. I want to remove my green. So I can do a paired removal if I want. So I remove one green and I remove the green from the other side, and it leaves me with 4 equals x. And there's the work I might show with that. I started off with 5. I pulled away, I took away a 1, and I took away a 1, so there's it is right there in my work. I took away a 1 and I took away a 1, and so my answer is I'm left with 4 on the left hand side and x on the right hand side. And you can leave it 4 equaling x, that's fine. Again, another way of doing this, I start off with 5 equals x plus 1, and I want to remove my 1 red. I could, if I wanted, make it into a 0 pair by adding a red, and therefore I'm going to make another 0 pair by adding the red, and now I've got 2 0 pairs, so those have effectively gone away, and now I'm left with 4 equals x again. And again, that exact same work is I've added a 1 and I've added a negative 1. So if I want, I could write it this way, where I've added the negative 1, and on this side I've added the negative 1. So I have add negative 1 and add negative 1 in my work. It's the same thing as showing that I've removed a 1, and so it works either way. So both questions in both techniques work just fine. I strongly encourage you as the teacher to make sure that you have questions with the x's on both sides so that the students are familiar and comfortable with moving numbers around from both sides. So I think I'll stop here. One-step equations, we've removed either an adding or a subtracting of something, and in the next video we'll talk about one-steps that require multiplying and dividing.